Okay, now now this is start record. Okay, next time if I haven't started recording, please try to remind me because otherwise, this is the normal class time. But if we go into the extra time, well, extra class, like the time I add, probably I will have less people can attend the class there. Yes, we will have the class, we will have the quizzes, but maybe not 15. 15 is too much. But we will have one quiz today, so probably we will do that at the end of this lecture. And yeah, for the extra classes, no, we will not have quizzes because, not everyone can attend that class, so we will not assign any quiz during the extra class time. Okay. All right. Do we have more questions before we get started? Yes, this Thursday and this Friday, the makeup lectures are all in this week because this week we only have one lecture due to the hurricane, so we probably will have two. The quiz are based on what we learned today. I cannot tell you that but it's based on something you learned from this lecture. But I cannot tell you whether it's based on the content today or not. And it's also same for the futures lecture. Sometimes it's based on the content you just learned. Sometimes it's based on the content you learned before. So you will see after you have the quiz. Okay, now let's get started. Let's see if we have more questions before that. Okay, no, that's good. All right, so let me share my screen so everyone can see that. Okay. Okay, now I think I shared the screen and we will talk about convolution neural network today. So I think if you have learned about, if you're talking about deep neural network, and this convolution neural network is something you have to know. Everyone talking about CNN. So it is kind of like one of the must know topic in this direction. So we would like to cover it today. So we have talked about the fully connected feed-forward neural network. And we mentioned that in reality, probably we don't need to use that architecture. So there are several ways to revise that. And the convolutional neural network is one of the classical way to do that. So and this convolutional neural network is designed to solve the problem about how to do image related tasks such as image classification, object detection, segmentation, extra. Let's see. Let's take the image classification as an example. So for example, what is image classification? We input an image, a picture of image, and by the way, for all the convolutional networks, the image must be the same size. For all the not only the convolutional network, even the more advanced image processing neural network, we all need to make the input image have the same size. If it's not the same size, first you probably need to do some pre-processing such as cropping or stretching, just make every image at the same size, and then you throw it into the neural network. So first we need to put that the same size. For example, here the image is 100 by 100 pixel. And after we feed the image to the model, we will output some prediction. And we will have a label as before, I guess. And then we're trying to minimize, for example, the distance. Here we can use the cross entropy. So we have learned this before, like in the logistic regression, there's no difference between this cross entropy and the logistic regression for multi-target classification. So we just do that. So first, we need to think about what is image. Image, you can think of this as a 3D tensor. Don't be afraid by this term called tensor. You can think tensor is just a high dimensional matrix. For example, for two-dimension matrix, so we have two dimension, but here we need to add another dimension. So like, because we have three colors RGB, and we need to represent the intensity in each in each color. Like, for example, what's the intensity in the red channel, what's the intensity in the green channel. So we need to, for a color image, we need to at least have 3 channels. So we call it a 3D tensor. And for each dimension, for each color channel, the dimension will be 100 by 100. So you can think, okay, so for each image, like this, the size of the input will be like you can stretch each color channel like this dimension, this matrix into a vector. So you can stretch the red one into a 100 by 100 vector, and there's and then concatenate all of them together. So you can think, okay, we can represent an image as a very, very long vector. So we can use this as our input, all right, to the neural network. And the value represents the intensity in each channel. So first question is, can we solve this with the fully connected neural network we learned last time, right? So we think, okay, so we just have a very high dimensional input, and we will have the output as a classifier. So depends on how many class do we have in our system. We can have different number of nodes. So what's the problem of this fully connected neural network if we want to use that for image classification? Can someone tell me? Like, can someone make a guess? So what's the reason? So if the fully connected neural network can solve it, what's the problem here?
The input feature size explodes as you increase the input image size.
Yes, that's the first thing, right? The input image, the input size is large, and it will lead to what's the problem? The number of parameter, right? So what we really care about is a parameter. As we learned before, if you remember when we do the linear regression, if we have a model which is like a very complex model, if we have a higher order model, it will be easily overfit to the neural network. So the overfitting is a problem if you have too many parameters. And the second problem, this is especially a problem in deep learning, is that if you have too many parameters, it's really hard to train the network. If you do that, but if you train a network like this by yourself, you will find that, okay, you will think, okay, this is an easy problem to solve, but if you want to train that, you probably find it's not that easy because there's too many parameters and it's really hard to optimize everything, right? So this is even an easy problem, like this is only one layer. Suppose you will have several layers, and all the layers are fully connected. So that's the reason the problem cannot be solved very well by this fully connected neural network. So the question is, do we really need that? Do we really need fully connected? Especially for the image processing, we will talk about 3 observations. And based on these 3 observations, we try to simplify this neural network here. Let's see how do we do that.
Where is that 1000 coming from on like the bottom right-ish part?
So this is, suppose we have 1000 class, right? So we have like, this is just the assumption of 1000, but you know, like in reality, like for the ImageNet, we have much larger class. So this number can be even like, here is 1K, sometimes it can become 10K, right? If you have 10K class in your data set, it will be 10K, right? So number of remember the number of neurons in the output layer depends on how many class in your data set, right? So the 1000 is even underestimate of this number of neurons here. Okay. All right, do you have more questions before we get started, like talk about the detail for this 3 observation? All right, so let's see what's the first observation is that. Suppose that when you have an image and you want to do some, like for example, classification, or here before you do classification, maybe first you want to discover some pattern. For example, here we just want to do a big detector. Right, so when you do the big detector, the first observation is this pattern is much smaller than the whole image. Right, so if you want to detect this big, you only need to look at this region. Right, so because there's no big in other region, and the big usually is lying in a sub-region. It's not like it's like a big like, I mean, spread over the whole image. It's not like that. The big is usually lying in a local region. So if you want to detect a big, probably you don't need to look at the whole image. You just look at region by region, small regions, and then it can do the job. Right? So we think, okay, if we only want to detect this big, probably we don't need to connect to all the pixels. We only need to connect to subregions. So that is our first observation. And when we do classification, usually the way we do that is first, in the first layer, probably we just want to identify some critical patterns. For example, here for some neuron, the job is to detect the beak. Some neuron detects the eye. Some neuron detects the claws, and the other's tail, something, or some I don't know, some other feature of the bird. And the second layer is trying to combine. For example, for bird, we know bird has this beak, bird have claws, beak have eyes. So if this 3 input, like to the last layer here, this 1 is 1, the output of this 3 is close to 1, and all other at 0, we think it will be bird, right? So and the output will be 0, 0, 1, 0, 0. And if it's a tiger, probably it does not have beak, but it may have some other features, like some type of tail. And based on that, you decide, okay, that is tiger. So this is very similar to how human being identify bird in a similar way. So when you trying to classify what is this, you're also trying to detect some features, some patterns. For example, if I ask you to look at this picture, can someone tell me what is this? What is this thing? What is this picture? What's this animal here?
A cat.
A cat? Good job. Nobody tell me this is a bird. So the first time I look at that, I think it's a bird. And this probably you already see the result here. If you see a bird, stop drinking because it's a cat. Right? So this is a cat turning head like this. So think about why you think it's a cat. Probably you also look at the figure, and when you look at the figure, you think of some feature of cat. Probably the fur, and I don't know, you probably think this is the ear, but I think this looks like a beak, and maybe the eyes, some other features. You think this is a cat based on some pattern detection. So we're trying to apply this to our neural network, right? So we also think, okay, maybe for the first layer, we just detect some pattern, and the second layer we combine that, right? So this is how we detect that. And this, based on this observation, we can do some simplification of the neural network. All right, so this is our first observation. And our second observation is the same region may appear in different regions. All right, so let's see. For example, both of these are a picture of birds. All right, so for the first one, the beak is here. The second one, the beak is there. All right, so if you want to do a beak detector, I don't need to have two different beak detector in each reception field. So the reception field here means that the region you would like to apply this detector to. Right? So for example, here, if this is like a 3 by 3, like if you have a 10 pixel here, the input to this detector will have it will be, sorry, 9 dimension, right? So if it's 3 by 3, it will be a 9-dimensional input. And this one will also, this is like a 3 by 3, we will have another 9 dimensional input. So since the same region can appear in, since the same pattern can appear in different region, you don't need a big detector in different reception field. You can just use the same, big detector, because, I mean, when I say same, I mean the parameter are the same. If you have the same set of parameter here, you want to detect this big, you can use exactly the same parameter for the big appears in other region, right? So each reception field, we don't need to put a different big detector, and because they are trying to do the same thing, they can use the same set parameter. So this parameter sharing can also help us to simplify the neural network architecture. The third observation is subsampling, right? So if the target is just to detect a bird, we can do some subsampling. So maybe this is a 100 by 100 picture, and after we do subsampling, it will be 15 by 15. And although the quality of the image is not as good as the original image, but we can still do our job, like do the classification based on the subsampled image. So this is our third observation. Okay, based on these three observations, we designed this network called convolutional neural network. Let's see. So the convolutional neural network is like that. So we have two layers in the convolutional neural network. One layer is called convolutional layer, and the other one is called max pooling. So sometimes we can have other pooling technology. It does not need to be max necessarily. So it can be like mean pooling or other pooling. So you can just think we have a convolutional layer, pooling layer, and after that you can just repeat this. We can have another convolutional layer, another pooling layer. You can have this as many as possible, right? And the convolutional layer is decided by our first two observations. Do you still remember, like the first two observations? First, some patterns are much smaller than the whole image, and also the same pattern can appear in different regions. Based on these two properties, we design our convolutional layer, and based on the third of the property, like the subsampling does not affect like object detection, we decide the pooling layer. Right? Based on these three, we decide these two types of layers. And first, let's check what is this convolutional layer. You can think of this convolutional layer, so it's like a filter. Right? So we can have different filter, and the different filter try to detect some different pattern. And the size of the filter depends on really how large is the pattern, right? So so for example, here, if we just want to detect some pattern, which really is 3 by 3, we can use filter 1. And the third dimension, it depends on the input. Right? So if you remember, if we want to represent a color image, it will have 3 channels. Right? So the filter has to be 3 by 3 by the number of channels. So here is 3. So if it is a colorful image, the channel is 3, and if it's black and white, the channel is 1. So if the image is black and white, the filter it will be 3 by 3 by 1. Right? So this is the size of the filter. And each filter here trying to detect a small pattern. For example, we can give an example like this. If our filter here, the value in my filter, let's see, for one channel, for the first channel, maybe like this, it's trying to detect some features like in the input, right? So all this value here are some parameter you need to learn, right? So this is like you set this network parameter, and then you just training that with back propagation, and you learn this parameter. But here we just assume, okay, we have a network, and the value of the network is already learned. So assume this is a learned result. And this network, so here we just ignore the bias, and you can see I try to use the same color here in the filter, the value here, and the connection here, because this is the value of the network of the weight. For example, the first this is your input, right? So the first channel, the first input here is 1. Sorry, the first weight W1 is 1. The second W here is -1, right? So the orange one, and until the last one is 1 here, right? For this channel, for this blue channel here, right? So this is all the weight. You input the input. This here is the input pixel value, and this is the value of your weight. And the reception field here, like because we only look at this 3 by 3 pattern, so the reception field is a 3 by 3 by 3 by 3. 3 is the channel. The third 3 is the number of channels. So this is 27. So we have 27. The input number of input is 27 pixels. So the size of the reception field here is 27. Remember we said, okay, we can share the parameter like to different reception field. For example, if we want to detect something like in the first region, right? So we can use the same value of parameters. So here I just use the same color to represent the value of weight. So you can think, okay, if we want to apply a detector to this region, I have these parameters. And if I want to detect the same parameter, like same problem, same pattern in the other region, I can just copy all the value in this first region. For example, here, if this is W1, here I can use the same W1. Yeah, if I have W2 for this pixel, I can use the same W2 for the second pixel here, etc., etc. So you see, like, although the parameter of these two regions are same, but since the input are different, right? So maybe here some pattern existing, here some pattern existing here. So since the input is different, the output will always be different. And the output can be represented like this. This is very similar to our feedback network. We have some linear combination, and we have a activation function here. And similar thing happen to other reception fields. Okay, so this is like, if I want to detect some same pattern in different regions, this filter can share parameters. And for each region, I probably will detect more than one feature, right? So I can have a big detector, I can have a tail detector, I can have an eye detector, right? So this filter, if you want to detect different features, then this detector cannot share parameter, right? So I can use same set of parameter to detect one specific feature, right? For example, this is the big detector, and then I use this parameter. And if I want to do an eye detector, then I will use a another type, another set of parameters for I detector. So you can think, okay, so that's the thing is, okay, I share the same parameter for the different region, and for each region, I probably will have more than one filter. Right, so filter 1 is the I detector, filter 2 is the tail detector, filter 3 is the big detector, like this. So usually we have more than one filter because you need to detect the different features. So here we give an example that we will have 64 neurons, which means that we're trying to detect 64 different features here in this example. So this is a very typical setting. So we can have 64 detector for each region, and each of this detector will be shared for different reception field. Right, so this is our basic settings. And we can look at an example here. So for example, here we have two filters. So think about we have an image, and the image is a black and white image. And we put all the position like and maybe for black as 1 and the white place at 0. So this is my image. And this is my filter. So these values are unknown parameters. And again, we need to train that and learn this. Assume this is our learned result. We have this parameter. And these two filters are trying to detect some patterns in the image. So before we go to the details, like to apply this filter to the image step by step, can someone make a guess? Can someone just tell me, okay, what does this filter 1 do here? So what does this filter try to detect? What kind of pattern does this filter trying to detect here? Can someone tell me?
Is it looking for a diagonal line?
Very nice. Thank you so much. Right. And this one trying to look for a diagonal ones like this. And this filter 2 trying to look at this pattern. So let's see how do we do that. Right. If we want to apply this filter 1 to the image, what we do is we just multiply like the values in the input and the values in the filter like pairwise, like this 1 times 1, and then we add them all of them together. 1 times 1 plus 0 plus times minus 1 plus 0 minus 1, and we just multiply the value in this position and then add them together, and we will get 3, right, for the first position. And then the next step is we then apply this filter to a different reception field. Suppose we have a stride as 1, so we remove the input, the reception field to right for 1 step, and we apply this filter to this reception field. So can someone tell me what is the result for this region? What is the output?
1.
1, right? So you just times each of that to this. It's 1. Are you sure? Like the output of this times this is also 1.
It's a -1.
-1, right? Very nice. So because like all other places are 0, only these 3 positions are 1, 1, 1, and you times 1, 1, 1 with this -1, -1, and 1, and then add them together, you get -1. Let's just do a quick check. If you want to do that again, you make another stride, and if you multiply the value in this region and you filter, what do you get here for this place? Any result?
-3.
-3, very nice, right? So just to do that for each position, and you keep on doing that for all the position, and you will get a feature map like this. Right, so you see, what's this filter do? This filter is trying to detect this diagonal 1, right? And the feature map have 2 value, which is largest one. So we have a 3 here. This give us largest result, and we have another 3 here. And the reason we have this 2, 3 is because we have 2 diagonal ones here. right? So in this position, we have a diagonal 1, and in this position, we have another diagonal 1. So and then the output of these two regions, when it multiply with this filter, we get 2, 3, and this detect this pattern here, right? So that's why we see, okay, this filter is trying to detect the pattern of this. And similarly, if we have another filter, and this filter, let's see, we do the same process. Right, for the second filter, we multiply the input with the filter. What do we get? Can someone tell me what do you get here this time? What's the output?
-1.
Very nice. All right, so we have 1 negative 1, and if you do the similar process, you subtract and then you multiply, subtract, multiply, and you get all the features. So here, when you look at this, you get a 3 here, right? So if you look at the outputs, you have the largest value is here, right? So because you have this pattern here matching with your filter, right? So you see, like this process is very, if you remember what is a convolution in signal processing, what is convolution? You have one input, have another input, you reverse the other input and sliding this filter across the other inputs. That is a process called convolution. So here we borrow the idea. The only thing is we don't do the flip. You don't need to reverse the filter. You just slide this filter over the whole image and get this output. And this is this is very similar to the convolutional operations in signal processing. That's why we call this convolutional layer, right? So this is convolution. And the output of this convolutional layer is called feature map. So this is what we get. So suppose that, so here we have an example of 2 filters, right? So the orange feature map is for one filter and the blue is another filter. Suppose we have 64 filters. Then the output, this feature map, will be what? Will be 4 by 4 by 64, right? So you can think of this as the image with 64 channels. Right? So each image is 4 by 4 and you have 64 channels because you have 64 filters. Right? So you see, like the input image is maybe so here in this example we have, I don't remember, 1, 2, 3, 6 by 6. Right, 6 by 3, 6 by 6 by 3. So probably this is a 3-dimensional image. So this is 6 by 6 by 3, right? Because it's 3 channels. And then you do the convolution. The output of this convolutional feature map is 4 by 4 by 64. So you can think of this some image similar to the hyperspectrum image. You have a lot of channels here. So this, and the next step, if you want to apply another convolutional layer here, the next filter should be, so if you want to decide, okay, the pattern of the size is 3 by 3, then the filter size it will be 3 by 3 by 64, right? The last channel is usually depending on the input, right? Because so here you can think of this as input as 64 channels, then the filter should be 3 by 3 by 64. And so that's why, like, the last dimension, the number of channels is not depends by you. You don't need to design what is the last channel or what is last dimension, because it's already decided by the previous layer. Because you already put a hyperparameter here, you say, okay, I will have 64 filters in the previous layer, then then the filter of the next layer should be the last number of dimensionals should be at least 64. That's why, like, when you use PyTorch or TensorFlow to code, you probably will find out that as long as you specify the number of the filters in the previous layer, In the next layer, you don't need to set up the number of filters in the next channel will be automatically decided. You don't need to do that. As long as you decide the number of channels in the previous layer, the library will help you to decide the filter in the next layer. Right? So that's why you don't need to like hand coding this part. Okay, all right. So you see, like in the next step, the input, if this is like a 3x3 filter, then the filter here are trying to look at a larger region, right? So you see if the first layer trying to detect some small region, for example, like this part is so suppose this is your input. The first convolutional layer looking at the region like this, right? If it's a 3x3, we remember we look at this region and that and this region, this region. But in the next layer, if you do a 3x3 reception field, you are looking at a much larger region, right? So here, look at the blue square here. So if you still do a 3x3, then you are trying to look at a much larger region in the input. So this kind of tell us that even the first layer, right? Even the first layer are trying to look at the pattern existing in some small region. In the later layers, we're trying to look at the like much larger region, right? Because when you're trying to detect the eyes, as you only probably need to look at a small region in the image to detect the eyes. But you want to say, okay, this is, you want to do, say, okay, this is a cat. You probably need to look at the whole image, right? Because here we have eyes here, and we have some nose here. You need to consider all of them, combine all of them together, and then you see this is image. This is an image of cat. So that's why you need to combine all these patterns, because the pattern exists in different places, and you need to consider a much larger region. So that's why if you just apply several convolutional layers, the network can do this job automatically for you, because even this is a 3x3 dimensional kernel, it will look at a much larger region. So let's just summarize what is the benefit of this convolutional layer compared to the fully connected layer. So we see, okay, so if we have a fully connected feed-forward neural network, it actually can do the similar job, right? So think about this. For this convolutional neural network, we try to design the neural network that the same pattern, right? Same pattern share with different parameter. And we use the same parameter for different region, and we actually only look at a small region. So you can think of this convolutional neural network as a subset of the fully connected neural network, right? Because if you add this constraint that some parameters should be the same, and you just only look at the small region, you just set all the parameter of other pixel as 0, it will be a convolutional neural network, right? So you can think of this, if you only look at some reception field, and you set the parameter of all other places at 0, then you realize this target, right, the reception field, and you just make some constraint that we have some parameter sharing, that the parameter for same different regions are the same, then you have this parameter sharing property. So that's why you can think the convolutional neural network is a subset of the fully connected layer. And the good thing for the convolutional neural network is you utilize this property of image to simplify the network. The fully connected neural network can still do that, but it's not specifically designed for the image input. And the convolutional layer will have a large model bias. The good thing for this large model bias is when we apply this to the image, it has a good result. But if you apply to some other, input modality, probably it will not be that good. You first need to think about that this input modality also have the similar feature as the image, or not. If it has, probably we can apply this convolutional layer. If it's not, probably you need to go back to your fully connected layer. All right, so before I go to observation 3, do we have any questions here for these first two observations? Okay, good. Now let's go to the third observation. The third one is much simpler because you just do a subsampling. Right, so what is subsampling? The subsampling is realized by that. Go back to our previous example. If we have a filter, and after we apply the filter to the image, we get this feature net. Right, so the maxi pooling means that we trying to only keep one pixel, one output of each region. For example, here, for this two feature map, we only take the maximum value in each region. In this region, we only keep 3, and each region we keep 0. We can keep 3, and the largest one is 0. Sorry, it's 1 in the last region. It's like that. So the reason we want to do that is because, you know, due to this observation, we will have we want to make this network smaller, right? So currently, this pooling process is not necessary because we have a very powerful computing resource, right? So if you have so currently we not only have CPU, we also have GPU and TPU. Because we have such power computing resource, and we can handle much larger network parameter, right? Not much larger number of parameters, network parameter size. So the pooling is not necessary. This is only used for when you don't have a very powerful computing resource. So because, you know, like in the machine learning domain, one aspect is like one direction is thinking about how to revise the algorithm, and the other direction is how to improve the, you know, computational resource, how to improve the hardware, the TPU, the GPU, right? So when the another direction is how to improve the data quality, right? So as long as the, you know, the infrastructure is improved, it can come back and affect our algorithm. So because, you know, the TPU is based on the computer resource, this process, the backseat pooling, is not very useful for now, but we still try to talk about here, like how this helps. So this is called maxi pooling. So there are some other pooling methods, such as, you probably will ask, can we use min pooling? The answer to that question is yes, you can use other pooling method, right? So when you do the min pooling, for example, here you just find the mean value. Here probably will be -1, and here probably will be what? Also minus 1 point something, right? So some other value. The idea behind this maxi pooling is, you know, we're trying to extract some feature, right? So here we're trying to detect some pattern. Here we want to detect this diagonal 1. So as long as it detected, so we keep the maximum value is because, okay, we think this region detects this pattern. So we keep the maximum value. So in this region, since there's nothing detect, there's no this pattern, so we keep the largest one at 0. So if we only keep the maximum value, it means that we can always, you know, if we will not miss any important feature. So this is the idea of the maximum pooling. So let's put this together to see how this works. So first, remember, so after we have the convolutional layer, we have this feature, and after the pooling, we only keep the largest value. For example, for this feature map, we get this result. And in the next time, right, so we just repeat this. You can think, okay, we have an image, which is like in the first, we have a large image only with 3 channels, and after we apply one convolution pooling layer, we have a much smaller image, but a large number of channels, right? So you can think of the image becomes smaller and smaller, but it becomes very, very thick. All right, so then you can just repeat the process several times, and after that, you just flatten everything. Like after the pooling, you just flatten everything into a long vector and apply our fully connect layer. And after that, it will be all the same to our previously explained fully connected neural network. And finally, you have a softmax, and you have this output. All right, so this is the how we use the CNN for the image. And next, we want to talk about one application of this AlphaGo. All right, so everyone, I think I remember in the first class I asked, does anyone remember heard about AlphaGo? I think most of you raised up your hand. So this is a very popular application. So let's see how we use CNN and why we can use CNN for this application. So for example, first let's look at the input. Right, so the input of this game is like you can think of this as an image, right? So, and the output can be a classification, right? So the next, because the next move is you try to put another check here, like in some place, because there is 19 by 19 position, then you can think of the output as a classification with 19 by 19 different classes. So again, the fully connected neural network can be used here. You can just think about the input. You can just stress the input as a 19 by 19 vector at all the place with, there with some black checkers will be 1 and white with 0 and empty with some -1, some other value. You can just simplify this as a image, right? So, and do a fully connect neural network. But CNN can performs much better, right? So the reason we do that, intuitively is because it shares some similar features as image, right? So we design the CNN based on the 3 observations here, and let's see that this input pattern also have the similar features or not. So first, remember our first observation is some patterns are much smaller than the whole image. So when you play Go, some people usually also look at some patterns in some sub-region, right? So you only look at this. If you want to look at the pattern like that, you probably only need maybe 3 by 3 or other small region. So so first we also want to detect some pattern in the sub-region. And the second observation is the same pattern may appear in different region, right? So that's why this game also shares a similar property as CNN. However, subsampling does not affect the object. This is not true here, right? So in the image, if you do the subsampling, it's good, right? So it does not affect the final result. But the pooling, how do we explain this, right? So if you just do the subsampling of the whole game, the pattern will totally be different. So the pooling does not really make sense in this architecture. So let's see. So then I go back to the paper and trying to find out, okay, how to explain the pooling process in the game. So if you go back to the paper and read the whole architecture, it said, okay, the network is this size, and we use some 0 padding, right? And then what the kernel size, like the filters, so the kernel means the filter size. And then how many filters we have, like what's the stride, what's the activation function. It has a lot of explanation, but it never explains how does it do pooling. So the reason, and then if you go back to the code, you will say, okay, this network does not use pooling, right? Because pooling does not really make sense in this case. So although it uses CNN, but it drops the pooling process. So it also tells you, okay, when you want to use the convolutional neural network, you don't need to use the full convolutional neural network. You don't need to use both, convolutional convolutional layer and the pooling layer. You can revise the architecture based on the input feature. Right, so this is the reason why you need to learn the machine learning basic knowledge, because you need to understand why we design this network, how we design the network, and how to apply that. Right, so although you can use this network to solve different problems, you probably need to think about, can this network be used in the different pattern or not? Right, so okay. After that, we want to explain something, like we want to explain what does CNN learn, right? So we apply these different layers, and we really want to know what does CNN learn here. So one way we can do that is called gradient ascent. You can see, okay, you have a neural network, and you train the network like this. You train the convolutional layer and the maxi pooling layer. And if you want to know what does the network to really learn, you can do this. Right? So you have an input. This is your input, for example, for some feature map. So maybe at the first layer, the input is just the image itself. And then you apply you input, you feed this into one layer, and suppose the network is already trained, as the parameter is already specified. And you have this parameter, you have this input, and then you just you will have output. You have a feature map of this. And how do we check what does CNN learn? You do this by see, okay, I have a layer of parameter, and when I want to know what does this layer of parameter learn, you just instead, after you learn the network, after the parameter is fixed, you just trying to change the input. You see, okay, what type of input can maximize the output, right? So you can just, so this is like, now you think, okay, the number of the parameters in the convolutional layer are fixed, and you want to see, okay, what type of input can maximize the output. So you can just, okay, now what you do is just you do the similar gradient descent as before, but now you think the parameter are fixed, the input are something you need to revise, right? Because you're trying to find what kind of input can maximize the output. Can minimize the loss function. Right? So you're trying to find a good input which can minimize the loss of the loss function. So you want to so that's why, like previously, we do gradient descent to minimize the loss, and now we want to see what type of input can maximize can make the activation function fire, right? So we can see, okay, what type of pattern does this convolutional layer want to learn? So you're trying to find this input. So this is called gradient ascent. You just fix the parameter and maximize the output by revising the input. So after you do that, we can we will find what does each filter learn. So remember, so here we have 64 different filters, and for each filter, it trying to learn some pattern. For example, for this filter, it trying to learn a pattern like this kind of texture, and this pattern is trying to detect some like this, I don't know, off diagonal stride, like in this strip in this direction. So each filter is trying to detect some different texture or patterns. And then when you try to, this is the example of the digit classification. And when you want to do the digit classification at the last, you just combine this pattern. For example, if you have two image, like a digit 2, probably you need to have some pattern. Like this stride here, like in the upper region, and some stride here in this region, and some other stride here in this region. Right. So you see, like actually in the first convolutional layer, it does not really learn what is a pattern or what is a number. It's only trying to find some texture or some pattern. and then in the next layer, right? So if you after you apply the convolution and pooling several times, and if you try to maximize this activation function, right? If you want to maximize the output of this layer, you want to say, okay, what does each of this neurons learn? You will see, okay, in the later neurons, probably you can see some pattern of the number, right? So probably this is very similar to 8, and this is very similar to 3. Right, so you see, okay, so this just trying to explain in the first several layers, right? It's trying to learn some patterns, right? And finally, when you want to make the decision, you combine this pattern, right? You come, for example, the 8, you probably need to combine some lines here, some lines here. You combine these patterns and make the final decision. So this is a very clever idea to solve the results. Is like you fix the pattern and try to maximize the input. Right, so here you fix all the parameter, and you want to maximize the output of this this neuron, and with different input. You're trying to train a network to train the input to find, okay, what kind of input can make this pattern, make this neuron fire, and then you will find, okay, what is the pattern, what does this neuron really learn there. All right, so this is everything about CNN, and we talk about the CNN too, and we think, okay, how does CNN apply to different patterns? Actually, there are some more applications. For example, CNN nowadays are not only applied to image, we can try to apply that to other models, other modalities. For example, for the natural language processing. Right, so this is an example for natural language processing. As you input a sentence, for example, I like my new phone. And the output is a sentiment analysis. You say, okay, is this a positive sentiment, or is this a negative, or this is just like normal, right? So you see, when you trying to apply the convolutional neural network to other applications, first you need to think about the basic idea, right? So what is the pattern looks like? So if you want to do that, so first we remember, so if you want to represent this sentence into a vector, right? So first you need to embedding it, right? So you need to represent this I into a long vector, right? Like this. You want to represent love into another long vector. You want to represent mine here like this. Then the whole image, sentence can be represented like with a matrix like this. So you can think of this as a matrix. You can call this a sentence matrix. And then we need to apply this convolutional feature. But here again, you need to analyze the feature of the input again. So in the image, each pattern exists in some region. For example, a beak is here, a tail is there, a eye is there. So the pattern exists in some subregion. But here, we cannot do the subregion. So for example, can you do this? Like you put a subregion here, you put a subregion here. So can someone tell me, like if you want to apply the convolutional neural network here to the natural language processing, can you do this? Any idea? Can you still apply a filter? No. Why? Why?
Because you won't be interpreting the image, the word embeddings correctly.
Very nice, right? So here, because you see, like for each word, the whole embedding is like you need to consider the whole values in each vector, right? So because you cannot separate that. This embedding for each word is something like as a whole, you cannot separate that. So if you want to use convolutional network to natural language processing to work like that, you can still use the idea to stride the pattern, but you cannot like do a subregion like that. Every time you need to consider the whole thing, right? So, and then you stride this. That's why if you look at this feature map, our kernel size, you cannot do that like you cannot specify the kernel size like a small range 3 by 3. The kernel size at least it need to be the dimensional like d by something. You can specify like 3 words, but it at least to cover all the values in the vector representation of each word. And then you can, and later on you can do a similar thing, like you can do pooling, you can do the feature map. But pooling again, pooling you still can, you can not pooling in this dimensional, right? So this dimensional you need to look at this into a whole. You can only do the pooling in this dimension. All right, so this is how we try to apply the convolutional network to some other application. There are more, but I just give this example. And nowadays, the convolutional network can be applied to some other region, not only the image, not only the natural language processing, it can also apply to video, I mean the audio, and signal spectrum analysis in signal processing, and some other things a lot. Okay, good, very nice. So I think that is all for the May class today, and now we need to go back to our quiz time. Let me stop this and oh, I see some question here. So yeah, so if you have some question, please just speak, because when I share the slides, I cannot see the chat. Someone asked a smaller kernel size better. If it's too small, think about this. If the kernel size is too small, it cannot detect the pattern, right? And if it's too large, it lose our original reason to use CN. So usually there are some classical typical settings. For example, usually we do either 3 by 3 or 5 by 5. So that is something we usually use. It cannot be too small, cannot be too large. So how large you can use? Probably you need to like do several different things and see how other people use that. Use this, I mean, the prior knowledge and some experience to help you to select the best, kernel size.
Professor?
All right, so yeah.
Would you mind if I talk to you after class? I'm from your senior design, one of your senior design groups. I was wondering
Which
if we could
group are you in?
12.
Oh, yeah, so that is something I'm missing. So I talk to groups. I have specified the time for group 3 and 13. The only group I'm missing here is 12. So let's do this. So can we schedule a meeting together with all the group member of your group?
Yeah, Friday at 3 o'clock would be good for us.
Friday at 3 o'clock, 3 a.m. or 3 p.m.
No, 3
Oh,
p.m.
sorry, 3 p.m. Sorry, I'm in China, and 3 p.m. is 3 a.m. in my time. Can we push it a little bit? 3 p.m. this Friday, right? So I need to double check with my schedule. So this Friday, right? So 3 p.m. So can we push it to maybe 5 p.m.? Can you check with your group member?
Yeah, and I can check, yeah.
Yeah, can you check to them, like, let's push it to either 5 or 6, either 5
Okay.
p.m., 6 p.m. Yeah, sometime around that, it works better for me. So I will send you an invitation, like, let's use the VOOV for our meeting so we can talk. And by the way, can you also send me your divide and conquer files? Like,
Yes.
I think you have that, right? So
Yeah,
send me
should
that.
I email you about that?
Yeah, email that to me before the
Okay.
meeting so I can read first, and then we can, we can talk based on that.
Okay. Thanks.
All right, so let's go back to our answer. So I'm trying to open this. Oh, let's see, how can I do? All right, so can you see the quiz? Probably I need to edit the time.
Is the quiz on Canvas or somewhere else?
Yeah, it's on Canvas. So let's see.
I can see it.
You can see the quiz. Everyone can see that the quiz 3.
Yeah, I can see it.
Yes, yeah.
Can
Okay,
see.
good. Then please finish that. All right, so probably we will not have too many content for today. And after you finish the quiz, you can leave the class. Okay, just one more comment. So, like when we talk about the linear regression and the logistic regression, we talk about a lot of details. So here I want you to explain the difference in your own words in terms of what's the difference of architecture. For example, like which one is more useful for the classification problem, and what is the reason for that, right? So you just need to explain everything in as much detail as you can.
Professor, have you put the test up yet?
Yes, can you see that?
I cannot see it.
How about other people? Can someone see the test?
You have to go to the quizzes tab in Canvas, and it's called Quiz 3.
Good. So if someone can see that, that's good.
So you
Okay,
want
yeah,
us to
I
just
see
like
it. Thank
describe
you.
the difference between, and no problem. So the difference between linear and logistic, and then
Yes.
which one is better for classification and why?
Right. So
Okay.
y-
Is there
yeah,
anything else
remember
we should
we
include?
talked. Remember we talk about the difference in 3 respects. For example, what's the difference between loss function? What's the difference of these two in the in the trainings in the optimizer? Right, we talk about, we compare this in this 3 aspect in the class. You need to talk about that, and then talk about which one is more suitable for the classification problem.
So you're saying to talk about how we optimize the model. I mean, they're both optimized using the same technique, right?
Yes, that is something I want you to put there.
Okay. I was like,
It's better for you to write the equation, right? So you can see, okay, for this one, how it looks like. All right, so please submit that by the end, before the end of this class. It's 2:45. Right, so the due time is 2:45. So please submit that before the end of this class. Otherwise, it will be a late submission, and the quiz will be closed in 2:50, right? I will give 5 more minutes, but I will penalize your final result if you submit it late. So please submit that before 2:45. All right, so I think most of you have already submitted that, and I will stop the class here, and see you next time. What?
good day,
It's
Professor.
what?
Have a good day, Professor.
Thank you. Bye.
Bye.